in the first period, you'll probably have time to finish handout number 5. Those all you should have left if you've been doing your work are the synthesis ones at the bottom, and those are the tougher ones. You know that, but you can work together on that, and that's fine, and hopefully get those done. At the next period, we have a double today. I have the review sheet. Okay, you probably, I don't know. I mean, I'm not really sure. This class does have a little extra time in both periods. You might have time to finish this one. But either way, for tomorrow it will be due. So again, if you use the time I give you in this class, you really have no more than, on average, well, no homework most nights, and on nights you do have homework, you have like 15 minutes. So, all right, let's get the last guys here. This is number 9, ethers. Look at his formula. ROR, another way to link together longer carbon chains. Do you have that written down next to yours? All right. Another way to link together long carbon chains. Ethers, again, look very similar to some of the other guys we've seen, right? For example, most specifically for this guy, who we did a lot with. Okay, that's kind of like ROR, except there's a carbonyl group here. What do we call this guy? An ester. Even sounds the same, right? Esters, ethers. Going to be easy to mix these up, guys. You're at 9. We're going to get 2 more. We're going to have 11, I think. Or maybe 3, I forget. 2 more, I think. You have a whole bunch of these different kinds of organic functional groups, different types of organic compounds you can have. And the ethers are just 2 big chains. It could be small chains, but either way, 2 R groups, 2 alpha groups separated by an O. All right? You get a couple of properties for this guy, and then some nomenclature. First of all, the properties. These guys, a lot of these ethers are very flammable, dangerous. I don't have any, because they also are unstable over time and form peroxides. You will probably use ethers in college for an organic synthesis, Grignard synthesis. And it's one of the more dangerous things you do in college labs. But they are important solvents. Used in organic chemistry. So you kind of need to learn about them. And actually, they're a great synthesis reaction. Another good one. Another one like the ester. Remember the ester yesterday? I did another board. I did all 3 of those synthesis ones on the board yesterday. And the last one was the ester reaction. I like ester reaction. I like ether synthesis problems for this reason. You really have to think. You have 2 parts to an ether, just like you have 2 parts to an ester. So you got to synthesize this guy, then you got to synthesize that guy, and then you got to put them together. I like that about those guys. It makes you think more. Okay, if you have a simple linear kind of synthesis, it's a little bit easier. This guy's not really linear because you've got to get this guy first, you got to get that guy second, and you got to put the 2 together. All right, let's learn how to name these guys. There are 2 ways I can name them. There's a common method again, and there's the UPAC way. First, you can name the 2 alkyl groups, and then add the word ether. That's the way most people do this. Like you could have diethyl ether or methyl ethyl ether. Sounds like a listing. Methyl ethyl ether, right? But that one doesn't always work because it only works for the small ones where you have and that's what we usually use for the common names. But for larger ones, where you have branches coming off any of those R groups, there's a little bit. You have to kind of be specific about where that O is. So we can name them this way, and then I'll do some examples of each. This is the actual UPAC method. You name and number the shorter alkyl group with an oxy suffix. This is one of the harder ones to name. These are one of the harder ones to name. So you're actually treating the one of the R's as if he was just another substitution on another chain. The shorter one is like a substitution on a chain. All right? And then you name the other guy the normal way you always would. Name the longer alkane, just the way you always would. So I'll give you a couple of examples of that. I think I have room for some examples. How many do I have room for? 2? Okay, we'll do a couple of examples. All right, we'll start with an easy one. All right, I'm gonna reverse this a little bit just so I can get some more room for my two examples on the board, which you don't have. You have plenty of room there. All right. What would I call this guy? Both methods. You just name both alkyl. For a guy like this, you can just name both alkyl groups. It's not a problem, and just put the word ether after it. So I can call this guy. This is an alkyl group, methyl group. This is the ethyl group. So I can just call methyl, ethyl, ether. Okay, it sounds weird, but it works. Now, if I were to call it by the UPAC naming system, the systematic way, I would call this guy, the longer chain is the ethane. So that's the last thing I would write. And this is the methyl group. So I have to use an oxy suffix. So this guy would be called methoxy, methoxy ethane. Methoxyethane. Now, obviously, in a case like this, either method works just as well. But when we get bigger ones, which I'm going to draw next, you kind of have to use, and you're only going to be able to use the systematic way. Okay? So let me give you one. Now, with me drawing it, it's a little bit harder to see, but that's an O, not a C. Okay? Draw that whole guy there if you can fit him in there. I know it's not a big space left, but see if you can fit him down there. In this case, I couldn't just call him like ethyl something else ether because I've got to tell where that O is coming off. And I wouldn't be able to do that by that method. I've got all that other crap on here anyway. I've got like an ethyl group or a methyl group and everything. So what would I call this guy? Well, this is not both of them. This is one thing. This is one thing.
No, I know.
Well, you can't really, I'll just say it again. I'll just say it. I can't really call this guy ethyl whatever ether because I'd have to say where that O is coming from. So I'm going to number that guy according to this, kind of like I'm treating the methoxy as if it was a chloro. Okay? So if this guy were on a, well, here, let's just say a guy like this. If I have a chlorine on that guy, that would be 2-chlorobutane. If I have this methoxy on there, I have 2-methoxybutane. So, keeping that in mind, I would name this guy, I have to start from this side, 1, 2, 3, 4. 4-methyl, 1, 2, 2-ethoxy, and then the big thing, 1, 2, 3, 4, 5, pentane. Okay? Got it? 4-methyl, 2-ethoxy pentane. Again, here it is. Those of you, 1, 2, the longer chain. You find a longer chain. This is the longer chain. Count this guy as a substitution group on him. 4-methyl, 2-methoxy. That whole thing is just like if it was a chloro, everybody would call this 4-methyl 2-chloro, right? So this 4-methyl 2-ethoxy pentane. The ethoxy is just treated like another substitution group. Okay. All right. So these are a little funky. They're not easy. They're not as easy as like 2-propanone versus 2-propanal or 1-propanal versus propanol and propanal. I mean, they just change one little suffix and you're done. Maybe you number something. It's a little bit harder, but it's not that bad. All right. Let's get the one. Remember, I told you I like to use these guys for synthesis reactions, and so I'm going to show you the one synthesis reaction I've got to do. It's called the Williamson Synthesis, and it's a really neat one. It looks like this. It's on your sheet already. And the reason this is a good one, too, another good reason it's a good one, we learned recently, a while ago, you should all have this sheet in front of you. You're going to need it in a minute. If you look here, somewhere down Let's see what number it is on here. There are a lot. Well, I'm not looking for the ether reaction. I'm looking for the reaction that gives me this. I'm looking for what number to tell you to look at. And I'm trying to find him. I make sure he's on here. 11. Yep, there it is. No, wait. No, that's just speaking of alcohol. No, sorry.
No, Nikki was right. It's 24.
Oh, yeah, 24. That's the reaction for the ether. But that's not the one. I want to find the one where you're making this guy right here. And I'm hoping he's on here. Now, 24 doesn't make this. It makes this. That's what I'm looking for. What number is that on there? It's got to be here. And if it's not, we'll have to. There it is. Number 14. 14. Okay, I'm going to look at number 14. I had that a long time ago. Okay? And that M stood for a metal. You take a strong, a really active metal, like sodium, potassium, and lithium, and you react it with alcohols, and you get ROM. That's this guy right here, sodium. Okay, and he was called an alkoxide. Remember that word? I used it a long time ago? Okay. Well, you'll have to make him. You'll have to make him. You'll have to put the two together. But for one like this, where I'm just going to give you a quick example, all right, we'll just do him. So if I have this guy right here, can you finish him? If I gave you that much on the sheet, could you do him? Could you finish him, name him, and everybody that came with him? That's organic. You do that. Try it on your own. See if you can put those guys together. Keep in mind, synthesis reactions are kind of the hardest ones on the test, I think, for sure, because they require you to have to think, sometimes think backwards, and sometimes think in multiple non-linear steps. And that's not easy to do. It takes practice. A lot of you guys haven't even tried to practice in the first 3 worksheets. You've either copied the answers out of somebody else or just not done them at all. You can't really expect, it's kind of like a person who's, nobody makes the NBA by never shooting foul shots and never playing basketball. You have to practice. Okay? Some of you have not practiced these. Okay? They're not easy. This isn't the NBA, but it isn't going to be an easy test. All right, so I'm going to put these guys together. What's going to happen? The Na and the Cl are, no surprise, going to break off, and I'm going to get them over here, NaCl. And these guys are going to link together like that. Right? Everybody do that? I mean, and that's obvious. The nice part about this is, I think, really, there's no memorization for this part of the test. You have this sheet. It has all the reactions on it. Okay? No one has to memorize one of these reactions. Hard part is you just saw me. And I've been doing this for a long time. Now, granted, this is a brand new sheet. We've got it last year. I just made it up last year. I used to use a handwritten one. It was only some things were typed. Finally retyped it well. All right, so I wasn't sure exactly where they were. But the fact is, it's hard to find them because there's so many on there. It's really not easy to look for them. There's 26 on there. So you have to find the right one that applies. Once you do, the job's pretty easy. It tells you what to do. But there's still points to be lost. You have to name everybody. Can I name this guy? What would this guy's name be? 1-ethoxy propane, right? You see why? It would be 1-ethoxy propane and not 2-ethoxy propane, right? If it was not coming off of here. You see, wouldn't you all agree that this would be 2-ethoxy propane? You see? Right? You name the shorter one as an ethoxy, and then the longer one as just regular propane. Okay. Over here, everybody can name this guy by now. We know how to name him last unit, a month and a half ago. Chloro or 1-chloroethane. right? Now this is the one guy we only covered a little bit, was back under alcohols. And his name is, he's an alkoxide. He would be sodium propoxide. Okay, sodium propoxide. Wow. So if you're not starting to get a little worried with the test only a couple of days away, you should be, for some of you. Because these are, now imagine this. We're going to get to these in a few seconds. You're going to be doing some examples in the worksheet in just a few minutes. You're going to have to, I'll say like, make 1-ethoxypropane from, and I might say, start with an alkane and, an aldehyde or something. All right, how are you going to do that? Well, you'd have to find a way to make a chloroalkane from this guy, which isn't really hard, be only one step. Okay, turn the there's no way you can turn an aldehyde directly into that, but you can turn them into an alcohol, then turn an alcohol into that. Okay, and then you'd have to put the two of these guys together. So some of these could take 3, 4, 5 steps to get done. And by the way, if I showed you some of I may look for them after I turn the camera off, some of the synthesis ones in the back of my organic test from college, you'd see that some of them were, 8, 9, 10 steps, okay, that you would have to do. Okay, it gets overwhelming after a while. And back then, you won't, in college, get a sheet like this to be able to just look everything up. It does get easier as you use them and learn about mechanisms, how they're all very similar, but it's not, it still requires you to think about it. All right, good enough. That's ethers. Now, let's do aromatics quickly. We did a little bit with aromatics. I bet you were hoping I'd forgotten about this, but I didn't. Aromatics are guys that are substitute or derivatives of benzene. Remember benzene? Okay. Aromatic reactions, their most common ones are substitution reactions. Now we're on that last page I gave you before. And this is the last page of the chapter. Now we end kind of with a lot of notes here, but you have to remember, this is a long chapter, and we had a ton of demos and labs in this chapter. All right, a ton. The last couple of days have been all notes. And there's a reason for that, and worksheets. We're saving most of the notes and the worksheets towards the end here and getting to them quickly because the test is coming up, and the lab's not on the test. It's nice to do ester labs, nice to smell those things, nice to do the fermentation, distillation, soap lab. It's nice to do all those things and break it up, do demos in the fume hood. But when it comes down to it, you're getting 150 points on Friday. 100 points for the one test, 50 for the other. And they're all going to be on this stuff. It's going to be on the actual stuff you're doing, and that's why we're concentrating on this now. Maybe a little boring, but that's just the way it is. All right. They're also used in polymerization. You can link those benzene rings together. I showed you that when I first went over it. You can put those benzene rings together and link them. I'm going to show you a couple of reactions to these guys. We'll start with halogenation. And I can't, on my keynote, my PowerPoint here, I can't make a benzene ring as part of the general formula. I'm just using AR to represent some aromatic. And that's already on the sheet. All right? The aromatic will be a benzene derivative of some type. So if I gave you this, you could write that down. If I gave you that, and that's your example, that's underneath example 1. That's what I'm doing. Do I only have one example for that one, right? Okay, so that's underneath your example. The reason I have so much room there is that obviously the benzene rings are bigger to draw. A couple of things about this benzene ring. I had several people do this last test. Okay? This is not benzene. What is that? You do know. We spent a lot of time on it. Did all the conformational isomers of it. Cyclohexane, chair and boat, right. That's benzene. That's benzene. That's benzene. I can draw benzene a lot of ways, but this is not benzene. So don't just draw that. That's cyclohexane. Okay? All right. What am I going to get from that? What do you think? Well, it's pretty easy, isn't it? You're going to just add that chlorine. And remember, coming off of these, although it's not shown on here, but coming off of these is an H in each one. You don't have to show this because it's not necessary. You know, it's just drawing the stick figures. It's not necessary. But that is what benzene really is. What happens is one of those chlorines is going to replace one of those H's, and the other H and Cl are going to get together. So what I'll get on the other side will be, I think I have it, that, plus HCl. Pretty simple. Does it matter where I put the chlorine? No. Okay? I'm not going to take off from where you put the chlorine because it could have other stuff on here. But basically, I should be able to name them. This guy would be benzene. And this guy is what? What do you think that guy is? Chlorobenzene, or 1-chlorobenzene. It doesn't matter. I'm not going to take off. Right. Now, the two other guys I could actually see, you have to know the formulas for. Benzene was 1. Say I had that guy on here, and I did the same thing. And that would still be a CH3 up here, and I would put a chlorine anywhere, I don't care, wherever I put the chlorine. This guy is not called benzene, though. He is methylbenzene, right? Or, remember the name? Begins with a T? Toluene. Toluene, yeah. Toluene or methylbenzene, and then you'd have, 3 chloro, 1 methylbenzene, okay? If you did that. I'll do another one with one of those on there in my next example. All right. And you can also have the xylenes. You don't have to draw these, but remember those guys. Yeah, there's a lot of stuff here. You forgot all about this. This guy would be 1,4 dimethylbenzene, 1,3, and 1,2 dimethylbenzene, or ortho, meta, or para-xylene. Wow, all of that's still on here. Yeah, starting to get worried now, aren't we? Good. I've done my job. So I could have started with this. If I started with this guy, what would have been different? Well, over here would have been, you would have written down 1,2 dimethylbenzene was your guy on the left, plus chlorine yields. Wherever you put the chlorine, I wouldn't care if you put them here, 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 whatever. Let's say you put them over here. You would have got 4 chloro xylene, or 4 chloro 1,2 dimethylbenzene on this side, okay, and plus HCl. So these are the xylenes. A toluene would be with this guy right here. All right, that would be starting with a toluene. I don't care where you put the chlorine on the other side. I put them down there. I put them over here. I don't care as long as you name him, number them correctly. All right, last reaction, nitration. Okay, let's say we start with toluene this time. There's toluene. Now, there's an acid only I use. Well, not acid only me in the world, but only I use. I don't let you guys use it because it's really nasty. I told you about sulfuric acid. You've only used that a couple of times. I did it in the fume hood once with the sugar, and you guys used it with the catalyst as the ester reaction. Well, nitric acid, that's what this guy is. Nitric acid, he's nasty stuff. And I don't let you use nitric acid. I use it to mix up a couple of solutions, but not many. All right. If I don't have any. I got rid of all the toluene I used to have when I first got here. There's a lot of stuff that you shouldn't have around here. I had bottles of toluene. If I mix some toluene with nitric acid, I would get, well, look up there. What do you think I would get? I would get an NO2, and I want you to think about why this would happen. Okay. HNO3, right? We have, you can think of the HNO3, one of the H's from here, okay, all right, and the H from here, and one of these O's, right, would give you water. What's left over? Well, one of the O's is gone, both of the H's are gone, you'd have NO2 onto there, right? Nitro. It's called a nitro group. So that's what you get over there. All right. Plus 1. Now, how would I name this guy? I could name him two ways. This guy could be called methylbenzene. I think you probably can see that pretty easily. Benzene. Or toluene. And this guy over here would be called nitrotoluene. Or it might be what? 4-nitrotoluene or 4-nitro 1-methyl benzene. Okay? Make sense? Alright. I do show this one for a reason. You all have that copied? I want to show you something kind of neat about this guy. If you actually do this reaction and you get 3 nitros attached to here, his name would be 2, 4, 6. Don't have to write this down. Actually, I think I have it right here. 2,4,6 trinitrotoluene. What is 2,4,6 trinitrotoluene? I have a hint to it in the capital letters.
Oh,
No. Trinitrotoluene. TNT. That's how you make TNT. That's how you make explosive. All right. Take all you need is toluene, nitric acid, and you can make TNT and kill yourself. Another reason I don't have a lot of toluene in the back room. Okay. All right. Now that's the 2 reactions of aromatics I wanted to give you. The last compound, number 11 here. Thank God, we're finally done with organic nomenclature and different functional groups. It's called an amine. Now, what I mean here is, amine is a basic compound. All right, it kind of is like, if you think about an amine, he's kind of like an organic ammonia molecule. All right, same way ammonia acts to accept hydrogen ions. If you remember ammonia, he was one of the few bases we saw, the only base we saw, that doesn't have an OH in it. If you remember what ammonia was NH3. Don't have to draw this down, but it was NH3. And one of the reactions we saw with that was if we take hydrochloric acid back to Chem 1, and we reacted with ammonia, what you got was NH4 plus Cl negative. And this showed you that you can have acids and bases even if you don't have OHs, even if you don't have hydronium ions, okay, and OHs. You basically, what makes this guy a base is what does he do from here to here? What does he do with an H? He accepts one. Remember? Acids donate, bases accept. So this guy was our acid. You may remember doing stuff like that. And that guy was our base because, and you had to look at the reaction and see who was acting like the acid, who was acting like the base. This guy was acting like an acid because he donated his H. This guy was acting like a base because he accepted one. Well, amines are kind of like organic ammonia. They have an R there. And that's all I really wanted to tell you. I'm not even going to do any reactions with this. Your paper, if I'm not mistaken, yes, they all got shifted because of the printer. I'll just be one of you guys. See, I printed my lab report out. The printer did it. It was all the printer's fault, but in reality, it's probably my fault. But that's what they should look like. Okay, so draw those correctly on there. Because the R's are like all shifted all over the place. So the one on the left should look like this. The middle one should look like this. And just cross out any of the other R's that are kind of straight around there, okay? And if you think about it, it's like ammonia. If this, instead of being NH2 with an R coming off it, if this was another H, it would be NH3. That'd be ammonia. Same thing's true. And all of these guys do have bonds coming, off them like that. Okay. So that's what they really should look like. And we call these guys amines. They have a nitrogen. They act basic. This guy would be a primary amine because he's bound to one R, the R group here. This N is bound to 2. This N is bound to 3. So you have primary, secondary, and tertiary amines. So again, you should know what primary and secondary and tertiary mean. Seen that a couple of places. Saw that first under Markovnikov's rule. All right. Now I don't have any reactions for amines. I just want you to be able to recognize them. Okay. Believe it or not, this is kind of weird. I told you in the AP exam, there's not going to be anywhere near the amount of organic chemistry I've been giving you. You won't have to know the nomenclature I've been giving you. You're not going to have to know what I'm about to do in the next unit, all the mechanisms and polymers and all this other stuff I'm going to do with you. All right? You don't have to know all that for the AP exam. But here we are towards the end, the last minute of this chapter. But you will have to identify. One of the big things you will have to do is identify different functional groups. Amines are what? Carboxylic acids, alcohols, aldehydes, ketones. You will have to know that much. Okay? You're not going to have to do the reactions and the mechanisms that I'm going to talk about and have been talking about. But you will have to at least recognize this. That's why I threw these on here. Okay? All right.